Buenos días. Comenzamos con las actividades del segundo día y estamos en la sesión 4, Seguridad, privacidad y confidencialidad de la información estadística oficial. This is session 4, Security, Privacy and Confidentiality of Official Information. And this morning we have with us Sarah Giessing, to my right. Everybody is to my right. So Michelle Simarth, Aleph Dajani, okay, and Peter Paul de Wolf. Okay, so this is, I think, a very interesting session, mainly because we are in the National Institute of Statistics and Geography in Mexico, and we are very interested in particularly how to safeguard the confidentiality of our information while we give the most to the public. So let's start with the presentation. Each of the presenters have 25 minutes. We will start with Sarah Giessing. I will give a brief introduction of her. She has a diploma in mathematics. She's senior researcher at the German Federal Statistical Institute in the Mathematical Statistical Department. Her main field of interest is statistical confidentiality. She's active member of the European Center of Excellence on Statistical Disclosure Control and co-author of numerous conference papers, as well as co-author of several handbooks on statistical disclosure control. Sarah, the floor is yours, please. I guess it's on.
Yes, you can hear me? Yeah. Okay, first of all, I wish to thank the organizers for inviting me over to participate in this very interesting seminar and for organizing everything so perfectly, and especially for giving 25 minutes time slot, which is really nice. So, try to see if this works. Well, as statistical agencies, we publish summary statistics. That's our main business. And so to say, you could regard it as our traditional approach to open data. Well, maybe in the digital age we can improve a little bit on that. But anyway, those summary statistics are often released in the typical tabular structures and formats. And in those structures, we often have cells where the aggregate actually relates to just a single or very few contributors. And to protect their data, we can basically choose between information reduction on one hand, like through further aggregation or suppression of some cells, or on the other hand, perturbation. And perturbation can happen on the input side, that is in the microdata, or at the output side, that is directly applied to the data presented in a table. Now for input perturbation, there's a variety of methods in the literature, mostly developed for the purpose of making safe files for researchers, but some of these methods are usable as well or have even been invented to create protected databases as input for the tabular products of a statistic. But in this talk, the focus will be on the methods applied at the output side, cell suppression and output perturbation. Now, with the very popular cell suppression methods, what you need first are clear rules to define which cells are to be considered sensitive. That's the easy part of the business, although even here we sometimes get into very difficult discussions. But the real difficulty comes from the fact that we statisticians tend to release to almost every cell that we publish another cell that is even further aggregated, like here in this training course example, the row and the column margins. And to avoid that, suppressed sensitive cells can simply be recalculated by taking the difference between a row or column total and the non-sensitive cells in that row or column. We have to suppress some of the non-sensitive cells as well. These are the secondary suppressions, and computing secondary suppressions in a more or less optimal way is a very difficult mathematical and computational task. And fortunately, nowadays there is software to do this, like, for example, the Dutch open source package Tauargus. And with such a package, you can automate cell suppression. And then the typical process is like, well, you first have a planning implementation phase in this phase, which is an expensive phase because it requires a lot of expertise. The regular tabular output of a statistic is planned. Then we have to carefully analyze this output, looking at linking and differencing risks. We have to set up the cell suppression procedure and test it for those planned tables. And if we did a good job in this phase, then hopefully in the next phase, during actual data production, things go smoothly. The software assigns primary and secondary suppressions, and afterwards we can publish our protected tables. But what happens next afterwards is that often some users want more data, more detailed data, different tables. And when protecting those additional tables, we have to take into account, of course, the links to our publication, because it doesn't make much sense to, when we protect one of the additional tables, select a cell as a secondary suppression that is actually already published. But with this extra requirement, our software will often crash. Why is that so? Here's an example. Oh, I'm afraid you will not see that much. It's a little bit small. This is a Tauargus screenshot. In this view, you see the data. The data are some turnover data displayed in a three-way table, and in this view you only see the data for one particular district. In the rows there are some industry codes, and in the columns some company size classes. The cells in the margins that are marked green because they are not allowed for secondary suppression, because they also belong to another table that is already published. The cells in red are the sensitive cells that have to be protected, like the one here in this row marked yellow. And the problem here is that the only two other non-zero cells in that row are marked green, so not eligible. The cell in the margin, because it is already published, but why this interior cell, which is in this size class 1080? We can see that not in this view, but if we change the view and look at the data only for this size class 1080, again by industry code, and this time in combination with all the districts in that state, we see that our only candidate cell for secondary suppression is not allowed, because it is exactly identical to the margin, to the state level margin that is already published. And that's why Tauargus will not find a feasible solution in that case, because there is no feasible solution for that problem. And that's basically why cell suppression can be automated, but only up to a certain degree, only for fixed, pre-planned sets of tables. And that was what I wanted to say about self-oppression. Now, output perturbation. This involves some very simple methods like rounding frequency counts to the next multiple of, say, 10. More advanced would be random probabilistic rounding forms, and the next level is then random noise. There is a special kind of random noise method that attracts some interest in several countries around the world these days. Random noise based on a cell key method. It has first been developed by the Australian Statistics Bureau, and the Australians use it to protect their census tabular products and some other statistics. I don't assume everybody here is already familiar with this interesting method, so I try to give a short introduction. Well, when applied to frequency tables, it involves basically 5 steps. During preparation, you first assign transition probabilities for a certain original frequency to change into a certain perturbed frequency. And these transition probabilities ultimately define the statistical properties of the noise, like the maximum of the perturbation, unbiasedness, and a constant noise variance for all original frequencies. Also, during preparation, you add a new variable with univariate random numbers to the microdata. These are the so-called record keys. And then during actual production, when you count the frequencies for your table cells, you also sum up these record keys, and this way you get cell keys. And then the final step during production is the lookup. Actually, this lookup step is a kind of a function. Its input is a list of original frequencies along with a list of the respective cell keys. The parameters are the transition probabilities, and the output are the respective noisy frequencies. That's simple, but maybe some illustration. The first step was to set up the transition probabilities. In this example here, we assume that from 5 onwards, all frequencies are changed with exactly the same probabilities defined for frequency 4. And this is why this transition matrix has only those 5 rows. By the way, it's not that easy to set up a transition matrix that leads to the noise properties that you want. But meanwhile, we have an R package which can do that, and that makes it much easier. Now, on the right-hand side, you see the transition probabilities represented as a panel. And in this panel, each bar refers to one of the original frequencies. The colors represent one particular perturbation value or perturbation amount, like, for example, the gray is for 0 perturbation. The width of the bar pieces refers to the transition probabilities, as indicated, if you can see them, by those red arrows for the case of frequency 1. And the x-axis of this perturbation panel relates to the accumulated probability distributions. Now here's a little example with data on age and sex. And at step 2, we have inserted a column with random numbers between 0 and 1. Now at step 3, we count this small population by age and sex, and we also sum up the record keys, and taking only the decimal places of the record key sums, we get cell keys that are again between 0 and 1. And now we can do the lookup step. For example, the males in age class B have an original count of 3 and a cell key of 74. So we look up the 74 in the row for original frequency 3, and we find it is in the light green area. And light green means perturbation of +1, so our original 3 changes into a 4. And here's another example for an original 15, which changes into a 16, and an original 5 that remains unchanged. On the next slide, we have completed the lookup step for all the table cells, and then on the right-hand side you see the tables represented in the usual format. And well, if you see properly, that you will find that some of the perturbed males and females is identical to the perturbed total only for one of the age classes, for age class C, but not in the other age classes. This is no surprise. Like rounding, noise is not an additive method, so we get something like rounding differences. On the positive side, we have exact consistency. A cell that appears in multiple tables will, of course, always have the same original frequency, and by construction, the same sum of record keys. And therefore, the lookup step will always need to lead to exactly the same perturbation amount. So this has to do for introduction. Now you see, there is cell suppression, there's input perturbation, output perturbation, so we have many methods. And what might be good is to have some guidelines to help making good decisions. So in Germany, last year we have set up a list of evaluation criteria for tabular data protection methods with main subjects like disclosure avoidance, potential, information loss, data quality, accessibility and clarity, and last but not least, the cost effectiveness. And then we have written a document, and the document explains all these issues. And then for a selection of some method, in the document we do a rigorous evaluation, method by method and criterion by criterion, and everything had to be very complete and fair and well balanced in the argument, and in the end we had a very long document. So we tried to condense it in a summary table, but also the summary should be complete, well balanced and fair in the argument, so it still has 20 pages. And what I'm showing you now is not 20 pages, but just some small examples. Not a random selection of examples, but just examples. And the first example is on primary protection. With cell suppression, primary protection will depend a lot on the particular rules defined by statistics department. Whereas with perturbative method, there's always some protection because of the uncertainty created by the perturbation about the true observations. Now, secondary protection, cell suppression can give excellent protection against differentiating risks, but only if applied properly, and otherwise you may have some actual differencing and linking risks, as we have seen in the example. With input perturbation, on the other hand, All tables are exactly additive and consistent, and that means by definition there cannot be any differencing risks. With output perturbation, the differencing risks depend a lot on the particular method and its parameterization. What we can say in general is that noise has a much better risk-utility balance compared to deterministic grounding. And to prove this point, we did an evaluation of differencing risks for a number of variants of noise and deterministic grounding, using a huge databases with thousands of tables and almost 30 million table cells and an algorithm to do the differencing attacks similar to linear programming attacks. And this risk utility plot here shows the results. For disclosure risk, we've counted the number of cells disclosed, exactly disclosed in such an attack. And for this plot, I've put it on a log scale. And for information loss, we've computed Hellinger distances between the original and the perturbed values. The blue observations here refer to one of the noise variants and the red ones to the rounding variants. And what you see, if you see, that rounding to bases 3 or 5 really has the highest disclosure risk, and except for rounding to base 3, all the rounding variants also have the highest information loss. Well, the next criterion was that I selected is relevance. Where with output perturbation, it doesn't make a difference if for the performance of the method, if a table is part of the regular planned publication or not. Whereas with cell suppression, we have seen with additional tables there can be problems to the extent even that we cannot release them. And for those users and their request, this is of course a serious loss of relevance. Now, additivity. For many of our typical tables, you'd expect that the interior cells sum up to their row and total column totals. Except, of course, if there are some holes and gaps because of suppressed cells. With input perturbation, what you have is that even heavily perturbed figures still sort of look correct because they add up perfectly well. With output perturbation, the method is applied independently to the interior cells and to the margins, and that has a damaging effect on the additivity. And this is why we noted under the complexity and transparency item that especially with random noise, this non-additivity issue needs some special attention in the user communication to express it sort of politely. Well, the next item is publication flexibility. Flexibility is a very important thing in the digital era, I think. Here we observed again the disadvantage with cell suppression that it works well only for pre-planned sets of not too complex structured tables. And the last issue is regarding cost effectiveness, and here the IT productivity potential. Well, for cell suppression and also for many of the input perturbation methods, there are standard packages that do the computations, which sometimes are very complex. For random noise based on a cell key method, agencies have to build up infrastructure that integrates the simple computation steps that we need to add up the cell keys and do the lookup step into the tabulation packages that are used during the actual output production. And that's quite a challenge, I'm afraid. Rounding is much cheaper here because for rounding you don't need any special software. So I'm finishing now with a short summary. Well, I've mentioned or explained the basic concepts, kind of a process model and some obstacles with cell suppression. I've introduced cell key method based random noise, and in the end I've presented a list of evaluation criteria for tabular disclosure control methods with some instances. And thank you for your patience, and I'll be happy to answer any questions.
Thank you, Sarah. Now